Connected Components Workbench, industrial automation software. That is the subject of this series of videos, but more specifically using CCW with the Micro800 controllers. These two documents, it's actually one manual broken into two parts to make it easier to handle in class. Contains all the lab projects, all the hands-on learning for the Micro800. Now, Connected Components Workbench is a little bit different than other products that Allen Bradley Rockwell Automation has had in the past. In the past, you had RS Logix and you had RS View. And then you also had yet another software package for VFDs and another software package for motion, another software package maybe for safety products. So that type of scenario would be similar to starting a business that develops and sells one product. And over the years you made good profits, so you decided to take on another product. So you bought a company that had a product that fit within the venue or the strategy of your current product that actually complemented your current product. However, the buildings that you got with the new property don't match the buildings of the old property. So now you have two different locations, maybe in two different parts of town, two different cities, and completely different architecture, completely different support functions. Maybe you have electrical heat in one, natural gas in another, steam in one, etc. So the two properties themselves have nothing in common, but your company sells products based on what's produced in these two properties. And then again, you prosper and you buy another company with yet another entirely different architecture or building format. So now you have to maintain three completely separate support organizations and structures, but it's really one company, and you have three products that complement each other, like PLCs, VFDs, safety products, HMIs. So they're spread out all over the place, and there's nothing in common that supports the products other than one company makes all four products. So the change that Rockwell made with Connected Components Workbench was to buy one campus, move all the businesses onto that single campus, so you have one support structure for all the products. Now, I'm not talking about physical campus with buildings. I'm talking about software, operating system, and structure. And Connected Components Workbench is based on Visual Studio. Now, you may not like Visual Studio, maybe you love it, but Connected Components Workbench is a software interface using Visual Studio to all of these different hardware platforms. So all of our buildings have a structure that complements the function of what is within, not what is outside. So all buildings have a common support features or feature. Now let's talk a little bit about ladder logic diagrams. Some of this material is not covered in the manual, and then there's some of the manual that's not covered in the videos. So between the manual and the video, you should get everything. Rung of ladder logic, a single logical statement in the form of the traditional if then else. If this input is on and this other input is also on, or yet a third one is off, then turn on this output. Else, if that statement's not true, then turn off that output. So if it's in the form of if then else. And each logical statement is one step in the sequence. And it always ends with an action or actions enabled or disabled by the cumulative true-false state of the conditions. I know I'm reading a PowerPoint slide here, a bulleted PowerPoint slide. Okay, a rung branch provides a logical OR of any group of conditions, provides parallel output conditions. So you can OR the permissives, you can OR the read instructions, and you can parallel the output instructions. Now they both look like parallel circuits, but one, you are ORing the conditions to make the rung true. Once the rung is true, you can turn on multiple outputs by putting the output instructions in parallel. The 5 original instructions, and they look like a normally open contact, normally closed contact, a relay coil, and also latch and unlatch coils. Now everyone is familiar with normally open, normally closed contacts that are motivated by electromagnetic coil. Not everyone is familiar with latch-unlatch coils. A latching relay had 2 coils. And when you energized the latch coil, it opens the normally closed and closes the normally open, but it only requires a momentary pulse to energize the latch coil. Because when the contacts reach their end of travel, being pulled in by the coil, there is a mechanical dog or latch that latches the contacts in the not normal condition, meaning the normally open is closed and the normally closed is open. And it stays that way even with the coil de-energized because it's mechanically maintained in the not normal condition. Then there's another coil, a second coil. When you energize that, it pulls the dog or the latch back and releases the set of contacts, and the spring carries them back to the normal state. That would be latch output and unlatch output. And of course, Connected Components Workbench had to come up with new names, direct contact, reverse contact. So normally open and direct are the same thing. And in the newer Connected Components Workbench software, version 11 with the feature pack, you have a new menu that shows the XIC, XIO, and OTE name for these same 3 functions: normally open or direct contact, normally closed or reverse contact, energized output or direct coil. Now you've also got a reverse coil. That's a little bit different because both of these have a true and a false execution. The direct coil turns on a bit in memory if the rung is true. The reverse coil turns off a bit in memory if the rung is true. Now, you could do almost everything you need to do with just one of these. I don't see myself using the reverse coil other than maybe putting it into a lab project just so you can see it at work. And then, of course, the latch output and unlatch output, that is referred to as set coil and reset coil. Now that terminology is pretty old. That's been around for a long time. You also have OneShot instructions. In 500 land, you had the ONS, the OSR, and the OSF. one-shot rising, and one-shot falling. Now really, an ONS is a one-shot rising. The difference is that the ONS in some processors, some firmware, allows you a little bit of latitude in how you use it. But typically, a one-shot rising is what most people use. Or you can create the one-shot falling results by inverting the logic and then using an OSR or an ONS. Now, in Connected Components Workbench, you've got pulse, rising edge, and pulse, falling edge contact. And those behave exactly like the OSR and the OSF. But you've also got pulse rising edge coil and pulse falling edge coil. The difference between these two is the contact is just a condition that is in the rung that's true or false. With the coil, rising edge, falling edge coil instructions, you basically are incorporating the one-shot function right into the coil. So when the rung goes true, the rising edge coil it executes once on that scan and changes the state of that bit memory. But on the very next scan, that bit memory goes back to the other state. So you can do that either on the rising edge from false to true, or on the falling edge from true to false. Now, jump to label instructions are functionally identical as in all other controllers. So a jump to label allows you to use a jump instruction that is at the conclusion of a rung. In other words, if the rung is true, then it jumps to a label. And wherever that label is at in the program, whether it's in an earlier rung or a later rung, it will jump to that point. Just keep in mind, if you jump to an earlier rung, now you're jumping backwards in your program scan, and it is possible to create a continuous loop inside of the program, and then the watchdog timer times out and faults your program. So you want to be careful when you use jump to label and you jump backwards in a program. The return instruction is functionally identical to all the other controllers. In 500, 5000, it's not necessary to use the return instruction. When you get to the end of a subroutine, it automatically goes back to the main routine exactly where it left. On with our next lab. Just for fun, I'm going to switch over to a Micro850, which you see in front of you. Now, I've already created the project and I want to connect. And an interesting thing came up, so I backed out of it to show you this in case this happens to you. So I created my path through the USB, clicked on connect, and it came up and said fail to connect with control. The actual firmware major rev is smaller than the project. The project was 11. Upgrade the controller firmware using control flash to the latest revision, or create a new project that matches the controller firmware. So I could go back and recreate a project at 10. Obviously, I don't want to do that because I want to use the feature pack that came with 11. There's no reason to go back. However, notice it gives me a choice here, update firmware and download current project. So I'm going to click on that, and then I'm going to, it comes up, didn't even give me a chance to pause. Latest revision is only one bigger than 10, and that's 11. Update and download. Will not upgrade the digital signature scheme for the controller series. Controller is a 2080 LC50 48Q Rev A. Yes. Controller is not in the program mode. Please switch to the program mode for firmware update. There's a switch on the LC50 that I did look at, and it's in the center position. So I'm going to flip it to program and then back to the center position, which is traditionally what Rockwell does to put it in the program mode. Okay, so there's a 3-position switch on the LC50 right below the USB port. It was in the remote position, and typically actually I've never done this before with the Micro800, and not with the older stuff like Slick 500 where it was in the run mode. when I try to update the firmware. So this is probably standard fare, is that you have to put your controller into the remote program mode. So you go to program, then flip the switch back to remote. So this is going to take some time. I'm going to pause and then come back. It went through the procedure. I'm going to try to connect again. It looks like it lost the connection path when it flashed the firmware. I'm going to click on this, and it's going to bring up this. There's my USB port. And notice that it shows, when you see a red X like that, that means that the browser saw that unit before, but it does not see it now. If over a period of time you connected to a dozen different controllers, they would all show up here, but only the one that you actually have connected will show up without the red X. So we click on OK. Download project to controller. I did select to flash the firmware and download the project. I'm not exactly sure whether it downloaded the project or it didn't download the project. I didn't bother to go to check. It is downloading this time. We're not getting that message that we got before, that the firmware levels don't match. That popped up in my switching over from the LC20 with the HMI on it to the LC50. And we'll just go ahead and switch to the run mode just to see if we get any errors. Now remember, this is the first time. Oh, looky there. I didn't know that instruction was in that controller. I was looking at the LC50 in terms of motion control. The LC50 48.io QBB will support 3 axes of motion, stepper motors. When I was considering how I wanted to wire it up, because remember the LC20, I shifted the digital field device simulator input 0 to 5 to the actual I/O points 4 through 9. 4, 5, 6, 7, 8, and 9. 6 of them. Well, with this controller, I don't need to do that because it does not have analog. So that's also something that I learned. The only controller that I don't own is the LC30. And the reason that I don't own it is because I didn't see any way to effectively integrate Ethernet. And I really don't think that you want to be without Ethernet. I do have an LC10, which is what I did most of these labs with, to make sure those of you that are using an LC10 won't get left in a lurch. But I will be doing things eventually, if not already, that are cumbersome with an LC10. With an LC20, you have the best of everything, except that you do have to add, if you want a conventional USB port, you have to add the remote LCD screen, which wires into the RS-232 terminals in order to give you that USB capability. The LC30, I wouldn't bother. This is an LC50. I also have an LC70, which I did some of the lab projects with later in the manual. I'm going to delete this rung to clear this out for the sake of our lab and then come back. I had to go offline to delete all remnants of that axis. That motion instruction that I had put in there had been in support of a axis of motion. And if you go down to motion, you can add an axis of motion here. I had added it in axis 1, and it made it impossible to delete that using run mode change. So I actually went offline, deleted it all, cleaned it all up, and came back. So in the manual, this is what you're seeing, the 850. I have no plug-in modules and I have no add-on modules. You can actually extend this with couple modules, and you can plug in modules on the face. The LC50 QBB is a really nice controller, probably my favorite out of this family, and I do own all of them except the LC30, which I've explained before. I don't see an effective way to put Ethernet on an LC30. The LC20 with the remote LCD screen is probably the most bang for the buck unless you need multiple axes of PTO for motion, or some of the other features you're going to find in the 50 or the 70. So in the manual, I had you create a program, then I had you rename it as buffer inputs. We'll right click, go down to rename and buffer inputs. And then I had you open the global variables by double clicking. In the manual, remember that we are not looking at an LC50. So when I look at the global variables, I'm seeing a few IO and some system, and that's it. But this is an LC50. And remember, it has 20 inputs. So I'm sorry, 20 outputs and 28 inputs. So see, digital out embedded, digital output 0 through 19, that's 20. Then inputs, it's digital input 0 through 27. And then of course you have all of your system variables. What I had you do was go down to the bottom and click on that field and right click on it, insert record, and then I had you type in IN. Now I show it in capital letters. I'm going to use I lowercase n. It could be either, doesn't matter. And then type it as an integer. Now it shows up as a Boolean. It doesn't know what you're going to do with this variable. It knows the name now, but it has no idea what it is. So we're going to go select an integer. Now an integer is 16 bits. You could also do single integer, which is 8 bits. You could do double integers, which is 32 bits, but we're going to make this an integer. Now we're going to add a rung, so we go back to our program, and we're going to add a rung. We already have an empty rung one. And this product, as well as the Logix engine processors, like Compact Logix, Control Logix, if you open a routine or a program and there was nothing in it, it comes up with a blank rung, and that's what we have here. I say to drag a direct contact, but you see now with the newer menu, it's direct contact, examine if closed. So we can use either of those two terminologies. Personally, I prefer true if on. That instruction is true if the memory bit that it addresses is on. Because there's no memory location assigned to this new instruction, this pops up. Well, cancel this and then type in IN. Now remember that IN is a integer, so if I put a decimal point, it's going to pop up with the first bit of the 16 bits, IN:0. And that's our tag, IN:0. Then we also want to create a integer data type and name it out. So we go back to global variables, we go down to the bottom and we type in out. And we make that an integer. Go back to our program, add an OTE, direct coil or OTE. This comes up, of course, cancel that. Type in OUT, and when you hit the decimal point, it's going to come up with the first bit of that integer, and hit enter, and now you have a rung that addresses the first bit in an integer named IN, and an output instruction, a OTE, direct coil, that addresses a bit in memory, the first bit of an integer named OUT. Then I had you save and download this. So we'll save it and download. Download is complete. Change the controller to remote run to execute the controller project. Yes. Downloaded and online. I had you right click on this bit in memory, toggle Boolean value. So this goes true and turns on that bit. So really these are both bits, but they are one of 16 bits of an integer. They're not separate Boolean data types. They are an element of a integer data type. Okay, I had you save and disconnect. I had you add another rung of logic, so we'll pull one down to the plus sign. we'll put in and then we will go to variable selector, go to IO, and go down to our first digital input. Right there, digital input 0. And then we're going to go over here and put in a direct coil or an OTE. And I cancel this, right click, variable selector. We could have stayed with this up there just to have it. And then I had you put in in.0. So it would be simpler just to go in.0 enter. And then I had you switch this to out0, OUT.0, and this to digital output 0 from the module defined tags. I can backspace to bring up the whole list of variables and then pick the first digital output right there. Now the logic matches what is in the manual. So let's download that. Naturally, when I'm doing these recordings, I don't script them. I just take it as it comes, exactly the way I would do if I was working on a project. In this case, we're switching over from an 820 to an 850. Now, in the manual, it may say 810 because I might have done the project originally with a Micro 810. We're switching from the 20 to the 50. When I switch from the 20 to the 50, I now have a controller processor that it does not have the Ethernet configured. So although I might have configured the Ethernet port on the 820 earlier, now I'm switching to this 850. So I'm going to quick configure the Ethernet port and show you how I'm doing that, even though I may show you again later as part of a regular lab for doing RS links. But I'm going to throw that in here right now. You have to go offline to do this. You cannot do this online. We had 2 rungs of logic that we had just done, so you have to go offline. If you try to do it online, you'll see that it's grayed out. If you click on Ethernet, first you got to go to the Micro800 tab, in this case 850. It's going to pop up with the general parameters. You want to go to Ethernet and then scroll down, and this is the default setting. Obtain IP address automatically using DHCP. Now that's data handling control protocol. That's like boot P, except boot P always gives you the exact same Ethernet address, whereas DHCP leases you one for 48 hours from a server somewhere. So that means today you've got one IP address, and a week from now it could be a different one if you left and then came back. We want a fixed IP address. So we're going to click on Configure IP Address and Settings, and I'm going to punch in 100, 100, 100. I'll just throw in 181. Now it could be anything, typically from 1 to 254. Each of these 4 things here, 100, 100, 100, 100, 181, those are octets. They are 8-bit. So we're looking at this as what appears to be 4 decimal values, 100, 100, 100, 181. But in reality, it is 4 octets. 4 times 8 is 32. So you would be looking at a 32-bit Ethernet address. It's all ones and zeros. We haven't assigned the subnet mask yet, but the subnet mask defines the network address from the node or the individual port addresses, device addresses. If I left it like this with a subnet mask of 255, remember this is 8 bits, this is an octet. 8 ones is 255. That means that the network address is 100, and then these 3 octets are the individual nodes or addresses on the network at the address 100. But we don't use networks that big, so I use 255. Now, the network address would be 100-100, or 16 ones. And then the last two groups of octets would be the actual addresses. But I'm going to make it even smaller. So my subnet mask is 255, 255, 255, which is 8 times 3 is 24. The network address is 100, 100, 100. The actual device address is 181. So I leave the last octet of the subnet mask 0 to configure that last octet to be recognized as the individual addresses, not the address of the whole network. So the whole network now of 0 through 255 right here, of which we use 181, the address for these 256 addresses here is 100, 100, 100. That's enough of Ethernet for right now. So I don't need a gateway address. And all that I did was I selected configure IP address and settings. I put in an IP address and a subnet mask. Now remember, if I change one of these octets in the subnet mask, I am changing the boundary between the address of the network itself and the addresses on that network. So we'll leave it like that and we'll download it, and I'm going to pause and come back. So we'll start the download, pause. Here we are back online with the 2 rungs of logic in our project. In the early projects of all of my manuals where I'm teaching the fundamentals of something, I have a variety of logic that is meant to provoke questions. And these questions, when answered, when you resolve them yourself or listening to me, gives you a better understanding and intimacy with the data table. All things that happen in a PLC really happen in memory, in the data table. Everything centers on the data table. All roads lead to the data table. That includes the I/O interfaces, the programs that you write, anything that comes externally through the communication ports from HMIs and other devices, variable frequency drives that you're controlling. Not only do you send signals to VFDs, you receive information back from VFDs that you can use in your logic to better control the VFD. Same thing with motion control. We have this chunk of memory, and in front of you, you have 4 unique memory locations. 2 of them are obviously I/O. We have 2 tags here that begin with _IO, and if you don't already, you would recognize these immediately as actual bits in memory that are assigned the responsibility to reflect the state of either an input device, DI00, or the state of a bit in memory, DO00, that will automatically be transferred out through an electronic interface to a field device. Those 2 are definitely connected permanently as long as you have this program. They're connected permanently to the memory in that light. The other 2 are not. I purposefully put an IN.0 on an output energize, and then I put an out.0 on a true if on. Right below the digital input 00 true if on, and I put the input.0 right above the digital output 00. And I do this to emphasize that these are 4 bits in memory. You can write to any bit in memory, and you can read from any bit in memory. In the top rung, it reads a bit in memory that is controlled by a digital input, an electrical state of a digital input field device. And that rung, if true or false, controls the state of another location of memory that we have named IN.0. That dot tells us that it's the first. The dot tells us that the number following 0 is the first bit of a word. But that is a bit in memory. And the only connection that bit in memory, IN.0, has to anything, anywhere, is this rung of logic. The second rung reads the first bit of an integer named out. The fact that in implies input and out implies output is coincidental, and I did this on purpose. You will always use DI, digital inputs, the one in the first rung. You will always use that as a condition in a rung, a true or false condition. You'll read true if on, true if off. But in.0 has no connection to inputs or outputs. Only the name infers that it's an input, and yet it's in an output position. Just to make sure that you understand that only I/O tags actually, realistically, are inputs or outputs. Naming it in/out is nothing. So that's all I wanted to do with these two rungs of logic, and I had you switch them on and off to demonstrate that this has nothing connected to it other than I can toggle it on. This one is connected to input 0, and if I turn on input 0, you will see that go on. I'm going to flip the switch on the digital field device simulator, input 0. You can see it goes true, makes the rung true, and it turns on that bit in memory. But that bit in memory is just a bit in memory. If I go to global variables and go down to n, you see it has a value of 1. This is being displayed as an integer, not being displayed as bits. If we were actually going to look at the 16 bits, you would see that only 1 bit is on. In our second rung of logic, this is just a bit in memory and has no connection to anything unless I toggle, the rung goes true, and now I look over at my digital field device simulator and I see that output 0 is on, the light is lit. This should tidy up any thoughts in your head about the difference between the readable tag that's associated with an input or an output and a tag that you have simply named to imply that it's an input or an output. It's how it's actually used either as an I/O module defined tag or as a unattached bit in memory. But we're going someplace else here, and that is that this bit in memory right here, even though it's called an input, so to speak, the state of this bit, in.0, fully represents the state of this bit. So if we flip digital input off and on, the state of input 0.0 is going to follow the state of I/O embedded digital input 00. Consequently, this bit down here, if I toggle this bit on and off, the state of this bit, which is actually connected to an output device when you're in the run mode, this bit in memory right here is going to follow the state of this bit. Effectively, we're leading up to buffering I/O or memory mapping, in that we can use input 0.0 in place of this tag, and we can use this tag in place of that tag. So in our program, we can use this to represent input 0, and we can use this to represent output 0. So in other words, we can examine this bit in memory, and if it's on, a true if on instruction, we can use an OTE addressing this bit in memory, and we are using this as an input, this as an output. This rung right here buffers the state of this module defined tag. It buffers it into this bit. This bit, which we use as a conclusion to a rung to control an output device, it is now buffered to this output. This bit buffers that bit, and this bit buffers that bit. So this is input buffer, output buffer. I'm going to go offline, make some changes, and then come back. I'm offline. I'm going to add another program, add ladder diagram, and I'm going to rename it sequence. And in that program, I'm going to put a rung, true if on, and an energize output. I'm canceling that variable selector when it comes up because I prefer to do it where you can see the instruction. I want this to be input 0, so I'm just typing in input.0. You could, as soon as you press in dot and it comes up with 0 through whatever, but it's easier just to type it in and hit enter. And then I'm going to go over here and type in OUT, and you see that out comes up. When you hit the decimal point, then the bits come up. But I'm just typing it in, and now you see the rung's happy. I'm going to download and run this rung. Okay, here we come to the real story here. I'm going to go up and open up buffer inputs. Okay, I'm going to turn on digital input 0, and you see it turns on input 0. While I'm at it, I'm going to, well, you saw this bit come on too, and that's fine, because in our new program file, if I turn on input 0, you see it turns on input 0.0, which makes the rung true, and it turns on output 0.0. So if we go back to this, our buffered input and our buffered output, when I toggle on that switch, that other rung of logic is making the connection between input 0.0 and output 0.0, and that's why when you turn on that input or off, it controls the digital output. Then I had you create another program file, which I will go offline to do and come back. I'm offline. I created another program file like you did in the manual, buffer outputs. Now I'm going to take this rung and I'm going to cut it just like you would a word processor. I'm going to go to buffer outputs and I'm going to paste it. Now I'm going to do Control V, and then I'm going to delete this blank rung because we have nothing to put in it. Now the graphical user interface for Connected Components Workbench isn't perfect. I deleted this, and you see this much hangs in there. Now I'm going to try something. I'm going to go to Sequence and back to here, and you see that remnant is gone. Once you refresh the screen, those remnants of things that aren't really there anymore are gone. So here's what I have now. In buffer inputs, I look at the state of input 0, the screw terminal, through the memory, and reflect it into this bit in memory. In the sequence, I look at that bit in memory, and I use it to control this bit in memory. In the buffer outputs, I look at that bit to control the actual output device. So I'm going to pause and download this. And there you have it. Sequence, we call it sequence because this is your actual control sequence. And when you look at that, it just says input 0.0, true if on, input 0.0, and energize output 0.0. And if I toggle input 0 on, even though you can't see the actual input tag come on, it's turning on output 0, and although you can't see the actual output tag, the embedded digital output 00 come on, you can definitely see the light on your digital field device simulator come on, so you can see that this rung is working. But we have buffered the inputs and buffered the outputs, and there's a reason for doing this, which is explained in the manual, and it has to do with overcoming the non-synchronous relationship between updating I/O and running your program files. The last thing I had you do was to complete the entire group of bits to buffer all your inputs and all your outputs. I'm going to pause, do that, and then come back and show it to you and maybe throw in a few words. We have 3 things left to do to complete this lab project, and that is to expand our buffered inputs, our buffered outputs, and then throw in some more rungs in the sequence program file to test our buffered I/O. The first thing I'm going to do is go to buffered inputs, and I'm going to duplicate this rung. I click on it, and then I do Control C, and then Control V 5 times. 1, 2, 3, 4, 5. Now I have 6 rungs all alike. And if I click, single click, double click, single click, double click, single click, double click, single click, oh, I double clicked. It's a bad habit. With RSLogix 5000, you double click to basically get to the same point. So single click, and this should be 2, double click. I'm going to finish this off and then come back. So now you see I have the first 6 bits, first 6 digital inputs buffered into the integer word IN first 6 bits. Now let's do that with the outputs. Click on the head of the rung, Control C, and then Control V 5 times. 1, 2, 3, 4, 5. The reason I'm doing 6 total for both inputs and outputs is my digital field device simulator has 6 inputs and 6 outputs on it. In the manual, I only had you do 6 inputs and 4 outputs because some of you are using a Micro810 that only has 4 outputs. I'm going to go and do the same thing with these that I did with the others. Click, double click, click, double click, click, double click, and then click, output 2. I have all 6 outputs buffered, and I want to go to sequence and do something similar. I select the head of the rung, Control C, Control V, 1, 2, 3, 4, 5 times. Now in the manual, I had you do it 4 times and double up on some of your inputs to the outputs simply because you don't have 6 outputs. So I'm going to finish this up and then come back. Well, we'll do the first one. Click, double click, click, double click, and same all the way through. We have this all done. Now we're going to download it and demonstrate it. Buffered inputs, you see that we're buffering digital input 0 into IN.0 all the way down to digital input 5 is buffered into IN.5. In the buffered outputs, we have this bit, which is just a bit memory. It's a single bit of a 16-bit integer, and the state of this bit is buffered to output 0 and so forth down to output 5. And then in our sequence, we have something similar, but we're examine on or true if on input, go up to the top here, true if input 0 is on, or IN.0, and then energize OUT.0. I'm online now. If I take and flip on input 0, input 1, input 2, input 3, input 4, we'll scroll down here, and input 5, and vice versa, turning them off. That completes the demonstration of buffering your I/O. Now notice that we buffer our inputs and buffer our outputs in separate program files so it doesn't clutter up our logic, because this is not part of our logic and neither is this.